Rs. So what is the relation between these two things? See here, the total voltage VGS equal to, it is getting split across the two things, right? The total voltage VGS equal to V voltage VG dash S dash plus voltage across Rs. What is voltage across Rs? Current into the resistance. That is what is from Kirchhoff's voltage law it is given. So total voltage equal to, it is voltage in series gets split added, right? So VGS equal to VG dash S dash plus voltage across the resistance Rs. It is I into Rs. So GM into VG dash S dash into Rs. I can take this VG dash S dash as common. So I'll get VGS equal to 1 plus GM Rs into VG dash S dash. If you put Rs equal to 0 here, you will find that VGS will be equal to VG dash S dash. That is what this diagram is also saying, right? When you put Rs equal to 0, VG dash S dash will be exactly equal to VGS. Same thing, now we are finding the mathematical relation between, what is the relation between VGS and VG dash S dash. So now I can write the drain current IDS equal to GM by 1 plus GM into Rs into VGS. Or you know that 1 plus GM into Rs is VG dash VG dash S dash. So I can write it as GM into VGS by VG dash S dash. So if you simplify, I'm writing GM dash into VGS. I'm writing it as GM dash into VGS. So GM is the trans conductance without Rs, and GM dash is the trans conductance with Rs. If you include Rs, you have to put a dash. If you don't include Rs, it will be plain. So see here, so wherever this dash is going to come, it is going to include the effect of Rs. Rs is going to be your source resistance. So the effect of the source resistance is to reduce the effective trans conductance or transistor gain. You know that whenever you add a resistor, it is going to dissipate some energy in the form of heat. The actual effective power is reduced, correct? So whenever you are including this Rs, it will reduce the transistor gain because some energy will be dissipated in the form of heat. So GM is a function of VGS. So GM dash is also a function of VGS, and the graph of GM dash is shown here. So GM is going to be without Rs, and GM dash is going to be with Rs. So you can see the variation. So the variation is very simple. At cutoff condition, both the graphs are going to merge. Otherwise, when you don't consider Rs, the gain trans conductance is going to be very, very high. Because the resistance value, I am considering the resistance value Rs equal to 0. Okay, I'm considering the resistance value Rs is going to be equal to 0 for GMS, and Rs is going to be non-zero for G dash MS. I again say, please understand, whenever I write the symbol without dash, it means I am not including the effect of source resistance Rs. Whenever I'm putting a dash here, it means I'm including the effect of Rs in my equivalent circuit. So from the equivalent circuit, we have seen there are two limitations in Jfet. Okay, so from the equivalent circuit, they are saying that we have two frequency limitations in Jfet. First one was channel transit time. I told you whenever you have any medium, how quickly the majority carriers can cross the medium is a big challenge. Here in Jfet, we have a channel of length capital L. So how when the maximum frequency at which the device can operate will depend on how quickly the majority carriers can cross the channel. So that crossing time is given by a technical term called as channel transit time. So it is given by tau t. And you know, time is going to be distance by velocity. So tau t equal to length of the channel divided by saturation velocity. Saturation velocity is the velocity at which the carriers are traveling at the maximum speed. Okay, so you know the in Jfet, the channel length is of 1 micrometers, and assuming the maximum saturation velocity is 1 into 10 power 7 meters per second, then you will get the channel transit time to be 10 picoseconds. Okay, it is going to be 10 picoseconds. So 10 picoseconds means if you take this 10 picoseconds inverse, 1 by 10 picosecond, if you do, that is going to be the maximum frequency of operation of your device. So 10 picosecond, you know, pico is 10 power minus 12, correct? So when you take 10 inverse of 10 picosecond, you will get the answer to be 1 into 10 power 11. So the device can operate up to 100 gigahertz. So that's for such a high frequency, the device can operate. So one important parameter which decides the high frequency operating range of Jfet is the channel transit time. So lower and lower this channel transit time, your device can operate at higher and higher frequencies. So this is one thing which you have to consider in the design of your Jfet. Okay, and second is the capacitance charging time. So you have so many capacitance in your equivalent circuit, right? So see, this is the final simplified equivalent circuit involving CGD, and only these two are active at low frequencies. The effect is little bit significant at low frequency, CGD and CGS. So whenever you have a capacitance, the charging time of capacitance will also determine how fast your circuit is. That is called as the time constant tau. So we have seen in yesterday's class, right? So the time constant tau, that is going to be, it is going to be R into C. Whenever a capacitance is involved, the capacitance value is very high, then the charging time and discharging time is also very high. This will significantly reduce your high frequency operation of your device. You see here, in the simplified equivalent circuit, we have two capacitance CGD and CGS. And what they are saying is, as the frequency of input signal increases, these capacitance will act like short circuit. So in short circuit, current will be more. Because of that, the output current becomes a function of frequency. Actually, the output current should be constant, right? But it becomes a function of frequency. And at high frequency, the current starts reducing because of these capacitance effect. So two frequency limitation of JFET we have seen here, which limits the device from operating at higher frequency. One is channel transit time, which is the time taken by the majority carriers traveling at maximum velocity called the saturation velocity to cross the conduction channel of length capital L. That channel transit time has to be as small as possible for high frequency operation. Second one, even though we ignore all the capacitance at small signal equivalent circuit, but the effect of these two capacitance cannot be completely ignored. So the capacitance between gate and drain and gate and source, it cannot be completely ignored. And these effects will be seen in the small signal equivalent circuit also. And whenever you have capacitance, you have what is called as time constant tau. So the capacitance value, it is, if it is going to be very large, then tau value will also be large, which makes your frequency less. So at high frequency operation of JFET is going to be completely prohibited. So these two effects will stop the MOSFET or JFET from functioning at high frequencies. One is channel transit time, and second one is the effect of the capacitances. So any doubt in JFET equivalent circuit, please, if you have any doubts, please ask. Once we don't have any doubt, then we'll go for the MOSFET equivalent circuit. So I'm going to pause for a few seconds. If you have any doubts, please go ahead and ask. Okay, assuming that there are no doubts, we'll go into the small signal equivalent circuit of MOSFET. And you know that MOSFET has a special construction. You have a metal, oxide, and semiconductor layer. So we have to consider the effect of everything before drawing the MOSFET small signal equivalent circuit. So source and substrate are both tied to ground. Two capacitance will be already available in the device, which is CGS and CGD, but you have two more capacitance, which is going to be CGSP and CGDP, which are called as parasitic or overlap